I am Claudia Toci, and I am currently a fellow at ISO Garcin. So I will switch a bit topic from galaxies for today, and I will move to the beautiful protoplanetary disks. So for people that are not familiar, protoplanetary disks are materials surrounding young stars. They are one of the phases of the evolution of formation of stars. So basically you have your cloud is collapsing, is forming stars, protostars, and around the protostars, material is falling, forming a disk. This material is composed roughly 99% by gas and 1% by dust. And we are very interested in understanding what the dust is doing because we want to form planets. Our planet needs dust to grow in order to form. But we're also very interested in looking what the gas is doing, because actually we can have information on several layers of those protoplanetary disks if we change the tracers we use. And this beautiful image from the review of Anna Miotello of Protostars and Planet 7 is showing that basically if we change the tracer, so also the wavelength in which we are observing protoplanetary disks, we can have information, for example, in the mid-plane. If we look at large millimetric dust grains with ALMA, we can have information with the lines of the gas, so the emitting lines of the gas on the upper layers, again with ALMA. We can have information on the upper layer, upper surfaces using, for example, scattered light emission. And we are also trying to determine what's happening to the ices, for example, when ices melt to water, and all the chemical processes that are happening in protoplanetary disks. So our field is actually very active. I checked a bit on the schedule, and there have been some talks, and there will be any other talks that are focusing on different phases of stars and planet formation, or on higher masses with respect to the one we are focusing here. We are basically looking at solar-ish or a bit larger than solar masses of stars. So we have our protoplanetary disks, we have ALMA, we can try to see how the observations look like. And if we look how the observations look like, we understand that actually those protoplanetary disks are not continuous structures. Actually, in the millimetric emission, so these dust grains are actually concentrated in rings, for example. So we have rings and cavities, we have asymmetries, we have some spirals, and those substructures are actually revealed if we change tracer. So if we look at the upper layer of the disk, while with the millimetric dust grains, we are probing the mid-plane, so in the middle plane of your protoplanetary disk. And also in the upper layers, we see that the substructures are present. And so it's very, very relevant to understand what are the processing that are creating those substructures. But again, I want to spend 1 minute to focus on the fact that this multi-wavelength observation is crucial. Here I'm showing the same source, TW Hydra, with 3 different tracers. So if we look at the thermal continuum, so these dust grains emissions, we have a very compact, large for us, but compact with respect to the other emission. If we look at the spectral line emission, so to where the gas is distributed, is larger. And also the scattered light emission, so the upper layers, is revealing that this disk is actually larger than how it looks just looking at dust grains. So it's very, very relevant to study protoplanetary disks with multi-wavelength approach. We have plenty of mechanisms that can be capable to explain those substructures. I won't go in details here. There is a very nice review by Jayan Bai and collaborators, again, in Protostars and Planet 7. But basically, we can divide them in 2 different categories. Mechanisms that are capable to stop, physically stop, trap dust grains, forming rings, and mechanisms that are basically not stopping dust grains, that are actually expecting to drift inward because they are experiencing a different velocity due to a different behavior with respect to the gas. But again, it's a technical thing I don't want to enter here. And so those mechanisms may be due to different opacities in the disk. So maybe you can have a snow line, your chemistry is changing, and so your dust emission is changing. So you observe a ring, but the dust is still there flowing, while the other mechanism is physically stopping dust from going in the inner part of the disk. And we hope that at least a few of those rings and gaps are created by the presence of actual exoplanets, so young protoplanets embedded in the disk, interacting with them. And we hope to reveal them directly, because that is a solid detection. The direct detection is the most solid detection we have. So my job in the last years has been to try to bridge together the theoretical part of protoplanetary disks with the observation, and specifically using different tracers, so mostly ALMA observations in continuum emission and molecular line emissions, but also combining with scattered light informations from, for example, VLT sphere telescope. And I'm mainly using two different codes. So one is a three-dimensional code. And then when you have your physical model of protoplanetary disks, you also want to see how your model is when you're observing it with a telescope. So you want to post-process your model with a radiative transfer code and obtain a synthetic observation that you can directly compare with your real observation. But I'm also using one-dimensional codes with another radiative transfer code once we want to study a population of protoplanetary disks. Let's see if I can show you the results of both my works. So first of all, when we focus on large bright sources, the one I was showing you before, we have those beautiful substructures. And we believe, again, that a few of them, if not all of them, are made by the presence of exoplanets interacting with the disk. And specifically, I am focusing on sources that we believe may host multiple, at least two giant planets. So why giant planets? Well, first of all, because, here I'm showing, can you see my mouse? That basically our own solar system hosts two giant planets, Jupiter and Saturn, and we know from the NIS model that this is incredibly relevant in the evolution of the solar system. So we have also an evolutionary link with our own solar system once we look at the formation of systems with double giants. But that is also, a characteristic signature of the presence of giant planets. So giant planets, very massive planets, Jupiter mass planets, or even higher mass, are very relevant gravitationally speaking, so they can open a wide gap both in the dust and in the gas. So we hope to observe a gap in two different tracers, the dust emission and the gas emission. And this is a unique signature of high massive planets, because low mass planets can open a gap only in the dust, and the other mechanisms that I was referring before are not capable to open these wide and deep cavities in dust and gas. And also, once you carve a cavity, you can hope again for direct detection of protoplanets. So actually see your protoplanet. So we have a few sources we believe protoplanets are, and there is one in which we actually directly observed protoplanets, and this source is PDS-70. So here I'm showing several images. This is ALMA images, this is scattered light images, and this is MUSE images. And as you can see, one blob here, one blob here, one blob here, one blob here. So we revealed two giant protoplanets inside a cavity in dust and gas. Here is a sketch of how the disk looks like. So you have a dust ring, and then you have a gas ring, and then you have a cavity that is empty both in dust and gas. I modeled this source. I will show you some results, but also I modeled two other sources that we believe hosts multiple giant planets. And I want to show you this because, as you can see, two giant planets may have different impacts in the same protoplanetary disk. So in the case of PDS-70, two planets, one cavity, one dust ring. In the case of HD 169142, we believe there is an inner planet carving a cavity. There is a survival dust ring between the first planet and the second planet. This part is mostly empty by gas. Then you have an outer dust ring here, and again, some other gas. So in this case, we are preserving the ring in between the two planets. And in this other case, HD 100-546, we have an inner planet, a dust ring, and then there is a huge gap. This is 100 a huge gap. We hope that should be at least another planet here. And then recently we revealed another outer, very, very faint dust ring at 200 AU. So it's a morphology that is totally different from the other cases. So I want to show you what we do when we work in synergy between theory and observations. So the first thing you do your own model. So this is a three-dimensional simulation of the gas and dust of a protoplanetary disk. The blobs are the planets. And as you can see, those two planets are opening a cavity in the gas, because here the gas is all accreted, but you are preserving this outer dust ring. And this is a simulation that is trying to model PDS-70, the one with the cavity and just a ring. So you run your simulation, then perfect, you have several snapshots you may choose from, you select your best candidate, then again you have to, this is just physics, so you have density, dust and gas density, you want to add some chemical model, then you want to evaluate how the flux look like, and then you compare your model with observation. And this is what you obtain. This is an ALMA continuum emission, synthetic emission obtained from my models after post-processing them with the radiative transfer code MC-FOST. And this as a comparison from Kepler et al., the dust emission measured with ALMA. It's quite good. So then you can check if your model is reliable also on different wavelengths. So it's also the upper layer of your model are very well modeled. And this is the moment zero, so the gas emission, my model, the observations. It's quite good, but as you can see, I have maybe too much gas in the cavity. Not that much, then you touch the resolution of limit of your simulation and you can discuss. Then you can also try to have some models for the scattered light, but the scattered light is trickier than ALMA because it's not one-to-one. You're not actually measuring fluxes. You are post-processing your fluxes, so you have to treat your model as a real observation. So you have to post-process your synthetic image with the pipeline. This is the synthetic image, and this is the real image. As we can see, we are capable to reproduce the main feature. We miss some feature, and this is also very relevant because you can learn also from what you don't match. And specifically, here is clear, we miss the inner ring or inner disk. And so this is probably what is creating some feature here that we don't reproduce here. Then there is another thing you can do. So here I'm changing the source. Again, I'm focusing on the first one, the second one I was showing you, HD 169142. As I told you, you have two dust rings. And we believe there is one planet here and one planet here, and the ring is preserved between the two planets. Again, you do the same game as before. You do your simulation, you select your best snapshot. And here I wanted to show what is a best snapshot. So this is the distance from the star. This is the surface density, gas, surface density, dust, surface density. So two dust rings and a cavity in the gas. You post-process your simulation. And so those are my synthetic image. Those are the real image from previous results. So ALMA observations. Good agreement. You can devise new observation, and this is what we did. And recently we published a paper. Ian Hammond is a PhD student in Australia. He checked the sphere archival data, trying to look if we could look for a detection of this outer planet. Well, we have a candidate. It's super, super difficult to see planets, and this is why we have just a very few candidates detected. The PDS-70 I was showing you before is amazing. We see them directly, but we have another few sources in which we believe they are, but it's difficult to see. Then this is the third source I was showing you before, just to show you again what you can do with ALMA archival data, because this is a combination between two different ALMA data sets, and combining them with Davide Fedele and myself. So Davide combined the data, that obtained a better detection of this very faint outer ring, because please look at the contrast. This is 10 to the minus 3 level between the inner part and the outer one. So it's
2 minutes.
It's extremely difficult to reveal some such structure. This is the model. And again, you can try to use your model to see if you can have new observations to see, for example, if there is just one planet or a combination of multiple planets. And we asked for time at ALMA. We will see what we will get. Then again, one thing you can do briefly, this is not my work, is a work of a PhD student in Milano. You can actually try to look for giant planets around brown dwarfs, and also try to say something on the composition of your spectral indexes also in the modeling. So we are actually at a very high level of comparison between theory and observations. So super quickly, in 1 minute, there is one other thing we can do. And I think Francesco Zagaria will tell us more about this. So you can actually not only focus on bright sources, but also focus on population of protoplanetary disks. But again, in this case, it's extremely difficult to use ALMA archival data because you need the same sensitivity and sensibility once you go in population study. And the protoplanetary disks look like this. So not fancy at all. Dust emission, gas emission. And once you study them as population, you can do two different things. So you can try to say something on the global evolution of protoplanetary disks. So compare the models you have, my models, with observations. They are clearly not matching. And again, we learn something also by not matching. So the ingredients I didn't include, so substructures probably are there because we need to slow down the radial drift, so we need to match the models and the observations, or you can try to have analytical solutions from the theoretical results that are very old in the field and compare your simulation, your analytical results with other observations. And this is what I recently did in my last work. And basically you have analytical solutions, you have parameters, you can play with your parameters to match models that were previously tested with observations, and so have a better estimate for your parameters. And again, I think Francesco will tell us more something about this. And so quickly wrapping up, I hope that I convinced you that it's extremely relevant to perform multi-wavelength analysis once you do ALMA observations of protoplanetary disks, and to work together between theoretical astronomers and observational astronomers, because together we can actually understand better protoplanetary disks. And with this, thanks a lot, and I'm happy to take any question.